You might be live.
Are we live? Let me check.
Where's YouTube? Okay, who cares, whatever.
Slides are so stupid.
Okay, here are your slides.
Guys, just take a seat. It's not that deep.
It's because it's much more monitors.
Much more monitors.
Yeah.
It is okay. I have bought a second monitor. I will put it here. It is too big because I didn't measure my laptop.
Anyway, we're going to stand.
Stand?
Yeah.
I'm not standing.
You're sitting.
Yeah, I'm sitting.
Okay, is this okay?
Yeah, this is whatever.
Do you need to show the do you need to show high-cut window or
No, I don't.
everything inside?
I don't. Everything is inside.
Okay, nice.
Okay, we are starting now. If anyone didn't make it, that is their problem. Yeah, okay, so today we are talking about something that we forgot to mention last lesson, and then we are going to recap on voltage dividers and current limiting, just so that people didn't forget. And then we're gonna talk, the rest of it is talking about capacitance, inductance, and impedance. So yeah, last lesson had a bit of hands-on, but this lesson is unfortunately all theory. But do not worry, there is no math. So the reason why it's all theory is because the next like 4 lessons in a row are going to be completely hands-on in PCB design software called KiCad. And we wanted you to understand what you are doing before we started, because we are going to like say words and things, and then like you're not going to know what they meant if we started. Yeah. Okay, so capacitors, inductors, and impedance. Okay? Not necessarily in this order. Okay. Oh my god. Okay, suck it up. Okay, so basically, this is a screenshot from a electronics parts supplier. So basically, a resistor is not perfect, okay? When you have a resistor, you get like a 1.2 kilo ohm resistor, and this is fine. But then you will find that it is also has a tolerance of maybe 1%, 5%, sometimes 10%, although that's rare, because 10% is awful. And then you'll also find that it comes in a certain temperature rating. So this is supposed to say minus 55 to 155 Celsius. So generally, most components will have a voltage, a temperature rating of like not this wide, but a resistor is really simple, so it can survive a lot of things. Okay. Also, there's also a wattage rating. So I remember P equals to I squared R, which is the thermal power dissipation through a component from last lesson. So power dissipated by the resistance of a component, right? So the resistor is a resistor, so it dissipates a lot of power. So the amount of power that you have to dissipate, that's rated as well. So in this case, they all say 62.5 milliwatts. You can get like really big ones, but usually you shouldn't be like, don't. Yeah, usually you don't need that. Okay. Okay. Then other than that, the rest is kind of whatever. Yeah. So we wanted to mention that. Then why is everything just dead? Is it because of YouTube? Like, why is everything so blurry? No, it was perfectly fine on my Canva. I did not do that. It was absolutely fine on my laptop. Okay, yep, just suck it up. Okay, so voltage dividers, recap from last lesson. So everything is V equals to IR, and you just calculate accordingly. So if I have 5 volts and ground here, and I've got a 4 ohm and an 8 ohm resistor, then is the rest of the lecture like that? No, it's fine. Yeah, it's fine. It's just this. Yeah. Okay. I guess it's my fault. Yes. So we calculate the total current through the whole thing because we have the total resistance, and then based on that we can get the current through each resistor and therefore find the voltage across each resistor, right? So we did this last lesson. Something we wanted to mention was that we did a voltage divider last time to get a certain voltage in the middle, right? So it's actually way better to use not tiny resistance. Use a huge resistance. Use a huge resistance, you'll still get a voltage across this, especially if the voltage is not meant to carry a meaningful amount of current. If you just need a voltage for a reference, you can use a huge resistor and you will get like some insanely small current. This is 0.28 microamps, okay, with a 1 mega ohm and a 180 kilo ohm resistor. And you'll get, in this case it's a 0.5 volts here. So you can, if you use a way bigger current, way bigger resistance, you'll get way less current through your voltage divider, but you'll achieve the same effect. Okay. So this is quite ideal for anything that uses a voltage reference. Yeah. Okay, so that's all we wanted to mention, which we forgot to say last lesson. Okay, any questions about this? If you missed last lesson, it was just V equals IR. Okay, it was like primary school stuff. Don't worry. Yes. Okay, great. Oh yeah, current limiting resistor, forgot. Yeah, so when we put a resistor in series with the LED so that we limit the total current through this circuit. Okay, and also there's this like magic component here which we're going to talk about in like 1 second. So this is called a capacitor. Okay, yeah. All right. Okay, the lesson today is about capacitance, inductance, and impedance. Okay, and these are like the three problems with electrical engineering basically. Okay, so like all the circuits that you have learned in like primary school and like secondary school, like Kirchhoff's law and whatever, these are all steady state circuits which don't really change over time. In real life, your circuit is switching on and off, it is doing things, you know, the current draw is changing, and then we start to care about capacitance, inductance, and impedance. Okay, so we are going to be teaching these concepts now so that you can design circuits effectively later, especially because a lot of your circuits are going to involve things like microcontrollers and communication, especially for school projects, and those things turn on and off really fast, and these things will start to matter. Okay, so just for your initial FYI, impedance is the opposition to alternating current, alright, and it's basically the combined effect of resistance and reactance. Reactance being the combined effect of inductance and capacitance, and that's all I care about for now. I just want you to know resistance, inductance, and capacitance. These like magic words for now, okay? Don't know what they mean yet. These contribute to impedance, which is like the sadness. Okay? Any questions? Okay, there are three components of sadness, okay? Now we will learn about them. Okay, so we start with a capacitor. Alright, so we have, some of us have heard of capacitors. A capacitor is two parallel plates which are conductive, and they are separated by an insulating material, which is a dielectric. Okay, nobody cares what dielectric means. When you apply voltage across it, positive charge will accumulate on one plate and negative charge on the other. So I apply a voltage across this, and you will have positive charge here and negative charge here. Okay, basically I apply voltage and the charges will flow through the rest of the circuit and accumulate here. Alright, this is fine. Alright, so now I've got this like charge distribution across the capacitor, and I've got an electric field in between and a potential, which we also talked about last lesson very briefly, right? So the E field stuff was setting up for this lesson basically. Okay, so the capacitor stores energy in the electric field configuration, which is created by moving the charges around on the plates. Okay, so the more charge we store here, the greater the electric field in between, and the greater energy stored in the capacitor in the electric field configuration. You can think of it as like I had to do work in order to move the charges from one plate to the other. So that's work against the electric field, and then like the electric field can release that later as electric potential energy. Does that make sense? Okay, yes. So I apply a voltage across the capacitor. So this is me. I'm basically supplying energy to move current from here to here. So I'm moving charges from here to here, right? So that means that there's a lack of charges here and there's a surplus of charges here. So this is positive and this is negative. Did I fuck that up? I think I got the polarity wrong. You get the idea. I move charge carriers from one to the other, usually an electron, right? So then this becomes more positive, this becomes more negative. Alright, so then this configuration stores energy in the form of electric potential energy. Alright? Yes, in the electric field between these two plates. Okay? And that's like not the most important thing, okay? I just care about, look, there is charge stored here, and it is electric field, okay? That's all we need to know for now. Cool? Great. Okay, so the capacitor stores charge, and capacitance is how we quantify a capacitor's ability to store charge, or any object really. Okay, so the fundamental relationship is Q is C times V, which is basically just, which nobody actually cares about for now, okay? Like, I just want to tell you this, okay? So Q is the amount of charge, C is capacitance, and V is voltage. So basically capacitance says for a certain amount of voltage, how much charge can I store? That's it. Alright? So if I apply more voltage, I can store more charge in the same capacitor.
Yes, dependent on the capacitor.
Yes. So if my capacitor has a bigger capacitance, then I need less voltage to store the same amount of charge. Okay? Alright, great. Okay, so this is the only piece of math that like we really care about today. Okay, and like you're gonna use it exactly once and then never again. Okay? So bear with me. Alright, so current is rate of charge flow, right? It's like charge per second. Okay? So if we take this and we move it around a bit, and I don't care how you move it around, you get this capacitor equation where the current through a capacitor is directly proportional to the capacitance and the rate of change of voltage. Okay? So if the voltage is changing faster, there is more current through the capacitor. The reason why this is the case is because as charges move across the if charges move from here to here faster, because there is more voltage across here, that means there is more current, right? Because I apply a greater voltage, charges want to move faster, which means more current is there. That's it. Okay, so that's what that means. Okay, look, we have already like used the math. Now we don't have to care anymore. All right. So remember, when voltage is changing faster, there is more current. So current through a capacitor is not related to voltage; it is related to the rate of change of voltage. Okay, this is very important. Does everyone accept this?
Current through a capacitor is proportional to the rate of change of voltage.
Yes, and not proportional to voltage.
Because as the voltage goes up or down, the charge in the plate.
As charges flow, there is a greater voltage across these plates, right? Because the E field here gets stronger. So when current flows, the voltage goes. Am I making any sense right now?
Yeah.
We're good, right? This is fine, right? Current is proportional to the rate of change of voltage. This is the only thing we care about from that slide. Can? Okay, good. I will say this thing like 10 times, so it is fine, like during the rest of the course. Okay, so great. The faster the voltage changes, the more current flows. Alright, so how do we charge and discharge a capacitor? I really should have put a diagram here. Okay, so if the external circuit voltage is higher than the voltage across the capacitor, then the capacitor will charge. So there's a voltage across the plates, right? If I apply a bigger voltage than that, the capacitor will charge more. It will charge until like the voltage between the plates matches the external voltage. And if I put a smaller voltage across the capacitor, there's a bigger voltage between the plates than across the terminals. It will discharge. Okay? So if I have an uncharged capacitor with 1 farad of capacitance, farad is the unit of capacitance. Okay? So 1 farad is enormous, by the way. Like you are unlikely to see you will not be using a 1 farad capacitor. But if I place 10 volts across the capacitor, it will store 10 coulombs of charge, which is also huge. Alright? Now I disconnect the 10 volts. The capacitor is not connected to anything. It will retain its charge until I do something to it. Okay? Exactly. So the capacitor is kind of like a battery. Give or take, it stores charge. Okay? In that way, it's like a battery. So if I connect the capacitor to a lower potential, then it will discharge. Can?
So for the most part, charge will almost always be less than the initial voltage because of the capacitance being less than voltage.
Yes, that's right. So usually the capacitance of a capacitor which you are likely to see is going to be in microfarad or picofarad. It is not going to be in farad. Okay? Yeah. Yeah. Of course, you can find capacitors that big, but like there's not a lot of reasons to use it.
What happened?
Okay, any questions about charging and discharging? All good, right? Yeah.
What affects the rate of discharge?
Okay, so we decided to mostly omit this from the class today, but basically what affects the rate of discharge is this thing called the time constant. Joseph, you want to explain that?
Usually the resistance of the circuit and the capacitance. So the time constant is, so in a resistor capacitor circuit, which will be in the slides, it is as the capacitor discharge or charges through a resistor, the resistor will determine the amount of charge per time it accumulates that the charge will flow through the capacitor because the resistance You apply V equals IR in that case. Like if you just connect a battery to an ideal capacitor, it will just charge instantly.
So voltage you get the charge, and the way in which it charges
Based on the resistance, yes.
Yeah, later we will explain why it will not actually charge instantly, but yes, correct, essentially. So it will charge exponentially.
Yes.
Exponentially, but like backwards, right? Like
Decay
it will decay exponentially. Yeah.
Yes.
Okay, Ken.
Is it like based on the difference of voltage that affects the speed of the discharge? No, it's R and
Yes, that plays a role also. That plays a role also.
You were right, we should put it in the slides.
Yeah.
I thought nobody would care. Yeah. Okay, generally the rate at which a capacitor discharges, at least for digital circuits, doesn't affect you that much. We'll go through like one example of it actually mattering for you later, but usually it's more for like analog circuitry that we care about rate of capacitor charge and discharge, but that is out of scope of the course because this is a digital electronics course.
I can go through it after lesson if you guys want.
Yeah. Okay, so we good for this slide, right? Okay, great. Higher voltage charge, lower voltage discharge, no problem. Okay, we are going to talk about an application of capacitors now. So ignore the fact that the circuit looks complicated. We have gone through it last lesson. This is a full bridge rectifier, the star that me and Joseph both forgot how to draw, right? So this thing takes AC input across these two lines and then produces a DC output here, right? So the AC input is a sine wave like this, and then we take the sine wave and we flip the negative side so that it looks like this now. So this is DC now because the current because the current direction is not changing anymore, but it's still like a stupid DC because it's not constant, right? And usually like we want our DC to be constant so that we can like go back to using like nice and like friendly steady state equations like V equals to IR, right? So what we do is we apply a capacitor here across V plus and V minus. The capacitor will charge and discharge as the peak goes up and down. So when we are at the peak of voltage, the capacitor will charge all the way to maximum voltage, which is like whatever the DC voltage is, right? And then when the voltage tries to go lower, the capacitor starts discharging. Yeah, exactly. It makes up for it. So the capacitor will like fill up this trough in the DC graph. So whenever we're not at peak, the capacitor discharges and it forms this kind of like slightly less bumpy DC against time wave. Does that make sense? Yeah, it makes it flatter. That's right. So we call this like a smoothing capacitor. I mean, that's probably like a better. Is it a filter capacitor?
Yes.
I forgot. Yes, it is a filter capacitor. Good. Is it different?
People call it different.
It is a capacitor, and we use it for smoothing. Okay, everyone happy?
How do you select the rating to smoothen?
Okay, so usually when you are designing electronics, you will not be actually using AC. You'll be using some kind of like regulator or something which produces a spiky DC voltage.
You still have to select the capacitor.
Yeah, but I was going to say that usually the datasheet will say.
Yes. They will recommend specific capacitor
Yeah.
to use. But like usually, if you are concerned with the peak to peak of the DC waveform, you look at the absolute maximums. That determines like which choice of capacitor to use, and
The bigger the better.
the bigger the better. Yes, but
there are other problems with having too big of a capacitor because when you plug everything when you plug your circuit in, all the capacitors on your circuit are going to charge at the same time. So you have this huge inrush current, which is like, so don't use too big, you know. Usually bigger is not that much. Usually too big is not that much of a problem, lah. It's fine. Yeah.
bigger the better.
Just don't be ridiculous. No 1 farad capacitors. Yeah. Okay. So
So let's say if you have a AC between 0 and 1 volt, then your capacitor like input voltage would be like the average of that 1 to 0 volt.
no, the capacitor has to withstand the peak voltage because that is what it will charge to, and then after that it will discharge until the next peak arrives, and then it will charge again.
So don't be ridiculous.
So it has to be a bit lower than.
It has to be rated at greater than 1 volt.
Greater than 1 volt.
More than the peak.
Like the capacitor has to be able to withstand greater than 1 volt of voltage if you are going to apply a peak of 1 volt across it, right? It's not about the RMS voltage.
Wait. So like the capacitor, you need like it has a certain voltage that it has to start to charge at, which has to be beneath 1 volt.
Joseph, go and draw on the whiteboard. You use your finger.
Oh, we can use a finger.
Yes, it's a touchscreen.
So what's your question?
Wait, no, I'm just wondering like because if your capacitor, like let's say you have 0 to 1 volt, your capacitor needs to start charging before it hits that peak of 1 volt, right?
As in, when the
Yes,
very first time you
yes,
turn on, it will be
yes,
the
correct.
capacitor will be at 0 volts. So yes, the capacitor
Correct.
will charge first.
Correct.
Yes.
Yeah.
So probably it will look.
I thought it was it is a touchscreen. Annotate. Press the annotate button. It's at the.
On that side. On the
Ah, sure, yeah.
What's the problem?
Okay. Then. So like I mean when the capacitor charges it will look like this lah. This waveform, right? And when the capacitor charges it will look like this. So it's not exactly a sine wave per se. Then it will start like charging depending on the something like this waveform. Yeah.
Oh, okay.
Yeah. When you power it up lah.
This being voltage against time.
Yeah.
After the first charge, will it ever fully discharge? After it goes
Yes,
Oh.
because your load is still there. So it will discharge through the load when you turn it off.
So once you turn off the voltage source, which is the AC source, then
Yes.
at the very end of your there's still the load connected across your capacitor. So your capacitor will discharge through the load. It's no longer being charged at all.
Yeah, so this becomes the capacitor will discharge through this.
whatever consumes resistance.
Load can be
Anything
any.
with resistance. Oh, okay. So anything that sucks up the
Yeah.
Okay. Okay, great. These are very deep and important questions. It is good. It is good that you are asking these questions because there will be more questions later. Okay. So is everyone satisfied as of now? Great. No problem. Okay. Okay. Why is it not updating? Because we are annotating. Okay. So, Joseph, you teach this one.
Okay, so for RC circuit,
Louder, they cannot hear you.
yes. So for RC circuit, it is essentially the same circuit as before, but like in the discharge condition as you mentioned. So when the AC power source is not connected, the capacitor discharges through the load. So for RC circuit, essentially we can use it for when we want the voltage to rise slowly. Like so for instance when you boot up microcontroller and you want a pin to not instantly go high. So you can put an RC circuit on that pin so that the voltage slowly rises. Yeah. That is like one application you can use an RC circuit for. Yeah.
By the way, the reason why the microcontroller might need this is because the microcontroller datasheet says so. There is no like specific reason why this might be the case. Later I'll show you like an example of when we actually use this on a microcontroller. But basically, RC circuit is for having something turn on after a delay. We charge the capacitor through the resistor, and that is what causes the delay.
Yeah.
Because the resistor limits the current through the capacitor, so the capacitor can only charge slowly, which means the voltage across the capacitor can only rise slowly. So this voltage, reference to this, will rise slower because of this resistor and capacitor. This is what RC circuit is. Okay? Yeah, and then you can choose like specific R and C values in order to get the desired delay time given the input voltage and a few other parameters. Use online calculator, don't think about the math. Okay? Happy? Everyone happy?
It's like a mini drawing. Like let's say there's a 5 volts in, and then see the R, and like what does it do at the right side? Like, here this-
So if there's 5 volts in, is it?
Yeah.
So I'm just gonna draw blue now. So V in like goes from 0 to 5 instantly, right? So this is 5.
Or we assume it to be instantly because this is like our scope, right? Yeah.
Then this will be V in. Then your V out is gonna look like this. And like usually there is a point where it reaches like, okay, let's rename this to 6 volts for easier calculation. So there's a point where this becomes 4 volts. Why 4? Because the time constant, which is R times C. So this is the time constant. So you multiply these two together, you get a constant in seconds. After this time constant tau, the reach 4 volts, which is 2/3 V in. So that is like how long it takes to like reach this point. And usually, like we will assume after 5 time constants, he is fully charged already. Yeah, you get this?
This for the C, right?
Yeah. What do you mean?
Yes, this is the cost. This is the capacitor charging. This is how long it takes to
This
charge.
is how long it takes to charge. It's the same thing for discharging.
Okay, so when does the capacitor discharge? The capacitor discharges into V out.
In this case, the capacitor will not discharge until the circuit turns all the way
Yeah,
off.
in this case, the capacitor, if V
When
in
you
goes-
remove V in.
if the V in goes to 0, it will discharge lah. So like,
So basically, this applies a delay when you turn on.
so let's
Doesn't
say
do
the
anything
V
when you
goes
turn
to
off.
0, then it will start exponentially discharging. Then.
Will also delay the discharge.
It will, but usually when we turn off a circuit, we don't care what it's doing. Yeah. Yeah.
Something like this.
Okay.
This is to delay your voltage build-up, not to delay the current flow.
Yes.
Yes. There is another graph for current which looks like this. Yeah, because I am right?
So
Yeah.
actually when it's like at the beginning the current is high because the capacitor isn't blocking it, but then when it's full,
Yes,
the
yes.
capacitor
When
blocks
it's
it.
full, the current drops to 0.
Yeah, because they are like cancelling each other.
Yes, yes.
Yes, and yes, close enough. Yes.
Because the current,
Yes.
current flowing through the resistor is the same as current flowing through the capacitor.
Ah, okay.
Approximately, yeah.
Wait, what does it go after the down to the capacitor?
Which one?
I'm
Like it
so
goes
lost.
through the resistor and then down to the capacitor.
It goes, okay, so initially the current flows through here and then it stops flowing, right?
And it stops flowing because the capacitor has reached.
Because the capacitor has reached V in here. So initially the capacitor is 0. So as this charge, the capacitor V out increases. The voltage of the capacitor increases as it charges.
Which is delayed by the R.
Yes, which is delayed by the R.
So then once it they equalize.
Once they equalize, the voltage across the resistor is 0. So no current is flowing. Equals IR.
And then what happens?
What happens? The capacitor.
No,
is
then
charged.
nothing happens. Yeah,
lah.
yeah.
It's steady state AD. So it's at 5 volts AD. 6 volts sorry. Yeah.
Okay, can?
I'm a bit confused by the arrow. V in and V out.
Yeah. So from
That just says like where reference is.
this is the reference.
That's the reference, and then that's the
Yeah.
that's the topic.
Yeah, this is the convention for it. Usually it's like pointing this way. So you're measuring the heat of the arrow with reference to the tail of the arrow. Yeah.
Also the whole point of the thing is just to slow down the buildup of voltage in this.
Yes,
with
yes,
the
that's
R.
the whole point.
Yes, absolutely.
Yes.
Okay, so again, don't worry. There's online calculator. Okay, it's great. It's important to know the intuition of it. Okay, and then everything in like proper circuit design, unless you're doing like professional stuff, is like rules of thumb and online calculator. Okay, everything is good. Okay, all right.
You're using this for a microcontroller to like slow down when it turns on. Isn't that means that your microcontroller is limited by the resistor for how much voltage?
Not when it turns on, but for a logic pin,
Oh,
for
for a
instance.
logic pin.
Yeah.
Because if you use this
No,
for
you
power-
don't use this for power. No, you don't use
So,
that.
what's the internal resistance of the capacitor? If the capacitor is the one being
I'll tell you later.
That's the real world capacitor. Yeah. This is the ideal capacitor, so it's not a real world capacitor.
Okay, it is time to move on. All right. We can go further into RC circuits later, or like the terrible timing of like whatever. But like for now, let us continue. Any other questions before we move on? Everyone okay, right? Okay, so just FYI, capacitance of a capacitor depends on three main factors. One of them is the surface area of the parallel plates. So how much surface area of each plate when they are parallel, okay? Then the other one is the distance between the plates. And finally, the dielectric material between them. What is the insulator between the plates? Alright? I'll go over the dielectric material later. There are different kinds, and I just want you to know that there are different kinds, and like you can go Google the kinds yourself when you finally need them. Okay? But basically, I also want to talk about the fact that you can put capacitors in series and in parallel. So when you put capacitors in series, the capacitance halves?
When you put a capacitor in series, it decreases, it halves. If the capacitance is the same,
Capacitance is the same in half.
it halves.
Yeah, so capacitance decreases in series and it increases in parallel.
Opposite of resistors.
It's opposite of resistors, you're right. Exactly opposite.
Okay? Alright. Alright. So in real life, a capacitor has a few things that matter besides just the capacitance. So there's a voltage rating. Okay? Do not exceed the voltage rating, or like charges will just jump over the dielectric, and then like the capacitor is not hold.
That's called dielectric breakdown.
Yeah.
This is dielectric breakdown. In it?
Yeah. Yeah.
That's what I said.
It doesn't depend on the kind of capacitor.
Yes.
Okay, I could be wrong then. There is a voltage rating. Yes. What?
Aluminum and bromide gas are much better about this than ceramic.
Because ceramic is like the many layers, right?
So it's the material property.
Okay.
But it will break down at some big voltage, basically, yes.
Yeah.
Depending on the data sheet.
Yeah, so you don't push the capacitor all the way to its rated voltage, because like especially for ceramic capacitors, they will lose capacitors at high voltage, and sometimes your voltage spikes beyond like what you intended, and then the capacitor blows up. So don't do that. Alright, we'll talk a little bit more about this later, but basically just don't use it all the way to the maximum voltage rating. Okay, and I could be wrong about the details of why the voltage rating exists, but for circuit designer, we don't really care why it exists, we just want to use it. Yeah, so I might be wrong about this. Okay, then the temperature coefficient. Why did I put this? Oh yeah, if you're doing something high temperature, it could matter, but just don't do that. I'm gonna skip that. Yeah. Okay. So the capacitor has a resistor and a resistance and an inductance, and I will explain what inductance is later. But basically, the capacitance, especially the resistance. So Dylan mentioned a resistor earlier. So basically, every capacitor has like a secret resistor in series with it. Okay, and because the capacitor has some inherent resistance. All right, and this limits how much current can flow through it. And also how much the capacitor will heat up when you run a lot of current through it. Okay. Why do we care about inductance again? Like for capacitor?
Because it has a inductor in series with it, actually, like in real life.
Why is there an inductor in series with it?
Because of the traces of internally the
Oh,
capacitor
that
has
yeah. Okay, we'll talk about this later. This is just like regular inductance. Okay. Okay. So there are ceramic capacitors. These are the most common. They are cheap and small, but they need to be derated for voltage aggressively. Because the capacitance will drop as the voltage approaches maximum rating, and don't overheat it. Yes, correct. What? Yeah. Just basically like just don't push capacitors to the maximum rating, and like the bigger the rating is, the safer you are. Right? Give yourself more margin if like it's really important. Yeah. Physical damage. Yeah, the ceramic capacitor is ceramic, so it is like brittle. So if you flex it or if you mechanically stress it, it can just break. Also, the ceramic is piezoelectric, which is annoying because it vibrates. Not a lot, but like enough to matter for very sensitive applications. I might as well mention that, but like it kind of doesn't matter unless you have like an accelerometer or vibration sensor on your circuit. Yeah. Okay. Should have made a whole slide for that. Okay, and wait, any questions about anything I said just now? The last few slides. derating.
Oh, actually,
Absolutely none of my circuits are like this.
5 times. Oh, that's right.
Yeah, I didn't read it. Shame. Does anyone have any questions?
I feel like I missed something. What's the rating?
Derating means that let's say my capacitor is rated for 50 volts,
Oh, just use that.
and I expect it. Let's say I've like the wire that the capacitor is going to be connected to is like going to see 10 volts. Okay, I don't choose a 10 volt rated capacitor. I choose like 25 volts or whatever, something with a margin. Okay, because like without that margin, because when you approach the maximum voltage rating of the capacitor, like the capacitance of the capacitor will go down for reasons unknown to science. Nobody cares, okay? And then like yeah, so just don't push the maximum rating. All right? Okay, fine. We are going to talk about inductance now, but I'm going to build it up from like the physics because I think it matters. Okay? Yeah. Okay, so when current flows through a wire, we get this magnetic field which circles around the wire. The magnetic field is by right hand rule. Okay, so here is the current goes this way, therefore the magnetic field goes this way. Okay, because my fingers are curling this way. Excellent. Alright. And of course if the current goes the other way, then the magnetic field will go the other way as well. Alright? Happy?
Is there a reason it's only that there?
The reason is
By
please do
convention.
not ask. No, the reason is actually please do not ask because it is like some terrible like quantum mechanics or something. Nobody cares basically.
I asked
Yeah.
about the direction.
The direction is by convention.
By convention.
But the reason why the magnetic field exists is because of like some terrible thing which I wish I didn't Google.
Oh.
Yeah.
Yeah.
So it just is like that.
It's
Yes.
just by convention.
Yeah. Like we could assign all of the directions to be the other way and physics would still work. It's just that everyone has to put a minus sign
It's
now.
like how
Yeah.
electrons are negative.
Yeah.
You easily flip the sign.
Yeah, we just said so. Yeah.
Ask the dead man Michael Faraday himself.
Okay, so we have the wire with a magnetic field around it. So we can coil the wire and the magnetic field loop from each wire will sum up to like one huge loop all around. Okay, so the reason why it does this is both simple and irrelevant. So the magnetic field concentrates and amplifies and we get a stronger magnetic field for like the same current through the wire because the coil is amplifying and concentrating the magnetic field. Fair enough? Again, we don't care why, it just does it. Alright? When we make the current creates the magnetic field and energy is stored in the field. So a capacitor stores energy in the electric field configuration and an inductor, which is a coil, stores energy in the magnetic field. Okay? By coiling the wire more and more, we can store more energy in the field given the same current through the wire. Okay? Is anyone confused?
So more wire equals more field.
Yeah, more coil means more field, yes, for the same current through the wire. Okay? Okay. The dead man himself, right? So, so when you change the current flowing through a conductor, the magnetic field will change as well. Faraday says that if you have a changing magnetic field, that changing magnetic field can induce a voltage in another conductor or like in the same conductor. So basically, if I am a conductor and I am within a changing magnetic field, now I have a voltage. Life is just like that. Okay?
And it opposes the.
Next slide. Yes, next slide. So, so then we have Lenz's law, all right? And Lenz says that the induced voltage by the changing magnetic field is in the reverse direction, which means that the voltage will create a magnetic field that opposes the original changing magnetic field. So basically, whenever I change current through a conductor, the magnetic field changes. This magnetic field, which is changing, produces a reverse voltage in the conductor which fights against the changing current. Okay? So anything with inductance hates it when the current changes. It will produce a voltage that will fight against the changing current. A reverse voltage.
Does it cancel out or it just?
No, it doesn't cancel out. It's not strong enough, but it will fight against it a bit. Okay?
A lot in some cases.
A lot in some cases, yes.
Depending on inductance.
But never all the way, yeah. Will it ever go all the way? No, right?
No.
It can't. Not enough like flux,
No.
right? Yeah.
Depends on time also.
Yeah. Okay, so does everyone accept this?
So basically, so if you change it, there's some pushback.
Yes, correct. So whenever we change the current through a wire, this will, because of magnetism, cause a reverse voltage, which like reduces the change in current a little bit.
And the reverse voltage can be very high also.
Yeah,
It's
and
why it can damage your transistors if you like that. Never mind.
yes, reverse voltage can be big. Okay,
Very big,
yeah,
yes.
it can be big. Yes. Okay, is everyone satisfied with this?
But hang on, this only applies if there's an inductor in the circuit.
Yes, correct. So whenever we have an inductor in the circuit, it will oppose a change in current.
Yeah, probably easier to think about it is that for capacitors, they want the voltage to stay the same. For inductors, they want the current to stay the same.
Yes.
Yes.
Okay, that makes sense.
All good?
Yes, that makes sense.
Okay, great. Okay, so now we have the quantity inductance. So inductance quantifies the amount of opposing voltage generated whenever you have a certain amount of rate of change of current. Okay, and I put this here, but we're not going to use it. All right, basically, if you have bigger inductance, you will have more reverse voltage for the same rate of change of current. Bigger inductance, more reverse voltage if I didn't change the rate of change of current. Okay, so rate of change of current is what will affect the reverse voltage. Alright, the size of the reverse voltage, and the inductance can also affect that. Alright, okay, great. Any questions? Yeah, I put the same picture because I couldn't find a good picture of like inductance. Like just like I can just put a math equation there like, at best, so it's not worth it. Okay, any questions?
The inductor just refers to the coil or wire, or it can be any like conducting material within like near a circuit.
You are absolutely right. Yeah, it doesn't have to be a coil. So literally any
Any wire.
will generate a magnetic field when you put current through it, and that magnetic field will change when the current changes, so it will have inductance. Yeah.
Oh.
Okay, so everything is an inductor basically. Yeah, every single conductor is an inductor. All right, it's just that is it a big inductor or not? You know, so usually when you have a coil, then the inductance is big enough to matter. But usually for the simple circuits that we have been building so far, the wire, we do not consider that to be an inductor because like the inductance is so small that it doesn't matter. Ken?
But we put the current through the inductor. Right?
Yes.
Yeah. So I've actually said that wrong.
Yes,
Yeah.
I think so.
Okay. So when we do this on purpose, when we coil a wire on purpose, when we try and get a high inductance on purpose, we call this making an inductor. Okay? So an inductor resists a change in current and stores energy in its magnetic field. Okay? And here are some pictures of inductors, and like there's like what matters is that here's the symbol. It's like this humpy thing. Okay? I don't know. English is hard. Yeah. Okay. Great. So real world inductor parameters, you can just have a coil of wire, that's your inductor, right? But you can also put something in the middle of the coil. So we call this the core of the inductor. Alright? So like these have some of these have different cores. And there are different kinds of core, and nobody can be bothered to memorize the kinds of core. So like you can go and Google the core if you need it, but like usually like if you need an inductor, someone is probably telling you to use it and they will know. Okay? Everything is fine. Okay, then the wire of the coil has resistance, so you will have power loss through the wire because of heating of the resistance of the wire. So this limits how much current you can push through the thing before it just burns. Okay, and also for magic reasons, there is a maximum current of there is a maximum current where your inductor stops being an inductor. Okay, and I tried to understand it and I gave up. So basically, we call this the saturation current, and just like voltage rating, this is a current rating. Do not approach the current rating too closely when you are designing for your inductor. Okay? Yeah, so for example, on one of my circuits, I needed a saturation current of 5 amps, and I had to choose like some stupid giant 10 amp inductor, and it's huge, and it's like very upsetting. Yeah. What? I had to do it.
Only 2 times 18 months. again?
2 times is plenty, okay?
4.
No. Okay. Does anyone have a problem with inductors? Is everyone okay?
Just curious also. Like, what happens if you like have inductors in the magnetic field?
You know what?
In the magnetic field.
It's called transformer.
Yeah, that's what's
Oh,
so yeah, magnetic field can induce a current in like your PCB also. That's why there's EMPs and stuff. Yeah.
Yeah. Again, we didn't really touch that for this lesson because it's not really like most people are not going to design circuits that way. But like if you read properly into like the basic physics of like Lenz's law and Faraday's law, a lot of the worked problems will be things like, what if I take a coil and I just like start moving it through a magnetic field, you know? And then like you just see the coil dancing there, then you see your voltage curve dancing also. It's like that's basically what goes on. Yeah, it's all about Faraday's law and Lenz's law. Yeah. And you'll see things such as like, oh, I move a magnet through the coil, and then like the magnet encounters this like magic resistive force. The resistive force is like the Lenz's law fighting back, you know. And it's kind of elegant because the Lenz's law appears in like so many like ways. And like no matter what you do, it just fights whatever you were doing. It's terrible. Yeah.
It fights because the thing you put inside is like disturbing the
field.
It's like an energy conservation thing, right? If I'm not wrong. I don't really remember because it does not affect my ability to design circuits. Yeah.
In fact, two inductors like tightly coupled together. That's a transformer. So like that's what powers like that's how you can change
voltage.
the voltage.
The
Like-
voltage
like-
and voltage are. That's just how you
Yeah. So like in substations, there's a bunch of transformers there to convert high power to low power, etc. High voltage.
Okay, good. Okay, so just to recap again, the capacitors resist changing voltage and the inductors resist changing current. Okay? And for the remainder of the lesson, this is all we care about. Okay, so like we talked about how to apply capacitors. The way you apply inductors is like usually you don't. Usually like the inductor is already there and you have to deal with it. Yeah. Okay, don't worry about it for now. Okay. So okay, now we're going to introduce impedance. Okay, and impedance is truly like the reason why you have to pay electronic engineers enough money, because like otherwise they would not be an electronic engineer. So we'll talk about how wires are like not ideal. Okay, so in all our circuits so far, a wire just connects point A to point B just magically, right? But in real life, unfortunately, it is not magical enough, and like you have 1 million problem with all the wires. In fact, going forward, most of the whole back half of the course is about how to stop your wires from being terrible. Okay. All right. So a conducting wire connects point A to point B. All right. So usually we assume the wires have 0 resistance, but actually the wire usually simply has a low enough resistance for it to not matter. Okay. So really, this paragraph is like recap from last lesson, but basically the wire has a non-zero resistance because it is a conducting medium, and all conducting mediums will have some kind of resistance. Okay, so the wire has a non-zero resistance. Sad. Alright, now the wire is not infinitely thin. It has a cross-sectional area, right? So it has a surface area when you look at it from the side, and this surface area can capacitively couple to other conductors nearby. And then we form a capacitor between the wires. So here is the cross section of one wire, and here is the cross section of another wire. And you see this surface area here and here? You have made a capacitor, and now there is a capacitor here. You see this wire and this wire? There is a capacitor here and there's a capacitor here. You know, so now suddenly there are capacitors all over the place in my circuit. This is wonderful as well. Alright, so we call this a stray or parasitic capacitor. And the wire now has a non-zero capacitance. Alright? So if the voltage across the wire is changing over time, the capacitance will be like unacceptable, and like the capacitance between the wires and other surrounding conductors will resist the change in voltage, just like a capacitor normally will. All right. This wire is.
It's just a cross section of a PCB.
Okay, in this case, this wire is just really wide. Okay, like yeah, there's nothing special going here. It's like it's not going in some funny direction. They're all going in the same direction, but this one's just really wide. All right. It's my ground plane now. Yeah. Okay. Any questions about this? I have capacitors everywhere. Is this acceptable? It is not acceptable.
I still don't really understand where the wires are going.
No, okay, look. Okay, so this is the rectangular cross section of a wire which is going into the paper.
Into the screen.
They are all going into the screen.
I see.
Okay, so these are cross sections. Yes, so this is copper and this is copper and this is copper. Okay, and this is just like the PCB which is holding it together. This area here.
Oh,
And here are my stray capacitors,
because
which
the PCB is conductive?
no, this is just I don't care about this guy, I just care about the copper. Okay, so this copper to this copper, this is forming a capacitor because there is parallel surface area, and same here as well. And even these two, look, the side wall is a surface area, right?
Yeah.
So the sides of it will also form a capacitor like this.
And a capacitor is basically any two conductors separated by dielectric. That's
Yes.
a capacitor.
Oh.
And air can be a dielectric.
Why are capacitors normally round?
Huh?
That sounds.
Why are
No,
capacitors?
because they wrap the metal around each
When you
other.
open up the capacitor, those like electrolytic ones, it is basically like a long, giant, like long thing of thing. And you just roll it up and then it's just in a can.
Yes.
Okay.
Yeah, that's just just so you can have, it's just kind of like maximum like area within the thing as possible.
It's a chocolate cake roll.
Yes,
Yeah.
yes, it is a chocolate cake roll.
Alright, thank you.
Except that it's not edible.
And it has like two things at the bottom.
Yeah, powered.
It explodes. Okay, so the wire has a non-zero capacitance. Is everyone happy with this? No, I'm disappointed. Okay, when current flows through the wire, it generates a magnetic field around the wire, right? We just discussed this. So as Dylan pointed out, literally any wire can be an inductor. So therefore, the wire has a non-zero inductance. And if the current through the wire is changing, the wire's inductance will oppose a change in current. So again, usually the capacitance and inductance of the wire is small enough that we ignore it. But we are growing up now and we cannot ignore it anymore. Okay, so because of all of these factors, any real wire is not ideal. It has a non-zero resistance, capacitance, and inductance. So we now have to represent a wire with 3 additional parasitic components, which is like a resistor of unknown resistance. Okay, the resistance is quite known, but like then a capacitor of like unknown capacitance. And the capacitor can be to anything. In this case, I just put it to ground. Okay, this will couple to like literally any other conductor. So like if you got like 10 conductors running, you have like 10 capacitors. Okay, whatever. Then you have like an inductor in series as well, which is the inductance of the wire. Okay, so now these are really ideal wires connecting these parasitic components, and now you're properly modeling the behavior of your wire in your circuit. Make sense?
Transmission lines.
No. Okay, we group all of these factors together under an umbrella term called impedance. Okay, so basically, impedance is how we try to reconcile all of these together into something which we can use and we can like talk to people about without being sad. I mean, we'll be less sad when we talk about it. So resistance always opposes current consistently regardless of frequency. It's just where it doesn't matter which direction the current is going. It will still hit particles along the way. So it will still have the same resistance no matter what. But inductance will oppose changes in current, right? And capacitors only allow current through them if the voltage across them is changing. Remember? We remember this, right? So because of this, we unify all 3 of these as different ways that our impedance affects the current through our circuit. And in this way, we can like make it into something that's much more convenient to think about. Alright? It's a unified representation of opposition to current. And depending on what circumstance you are in, different sections of the impedance will matter more or less. Okay? But either way, you will have some kind of impedance, which means that the current will have to fight something in order to get through. Ken?
Basically, all the 3 things in the wire that make it not an ideal wire, just do like consider the impedance.
Yes, that's right. So all 3 of them are ways to like make the current like not what it was supposed to be, you know? So like the current has to fight either the resistance or the inductance or the capacitance, or all of them, or a combination, right? Yeah. And depending on what circumstance you are in, like a few or all of the components of here will matter.
So just basically like this thing in the impedance, it's just making it not perfect.
Yes, absolutely. Okay? Okay, any questions about this? We're not moving on until everyone is happy because like this is really important.
So inductors still, so capacitor still voltage, inductor still current from an ideal wire to non-ideal.
Both change in.
You shouldn't think of it that way because because let's say you have something that's turning on and off really fast, right? Yes, you will have like a voltage drop and a current drop across these components, but then they'll give it back in the next cycle. As you go from 0 to 360 in phase. So that's why we call this the reactance. So we have the resistance, which is just like it's just forever gone. Like the power is lost to the resistor through thermal losses. And then we have the reactance. And the reactance is where the power is lost intermittently. It's cyclical. And the power is given back by the inductor and the capacitor as we go up and down in an alternating current.
So the resistance will lessen the input.
Yes.
The inductors and capacitors will like move it somewhere else, but
Yes.
it's still there.
Yes, and it will come back later, like in like a different phase of the cycle.
But doesn't the inductor like do it like push back?
Yeah.
But it goes still back later.
Yes.
Yes.
If you want to think about the details of that, we can go over it later. It's the power factor shit, right?
Yeah.
So basically, you will have a sine wave.
The inductance will go up, the capacitance will go down.
They will not cancel.
Yeah, but like won't do it, they always be like opposite.
They'll be in different directions, but like as in like one will increase and one will decrease as frequency increases. Yes. But they will not. But the magnitude of them is absolutely not
They
going.
don't-
Yeah. Yeah.
It depends on what's the other factor besides rate of change, like the properties of the material of capacitor itself.
Yes, exactly. So like in this case we're talking about like a non-ideal wire. So it's not got like all of the capacitor like voltage rating and whatever. It's just a wire, right? But it still has a capacitance, right? So depending on whether the capacitance or inductance is dominating, you can have one or both climb like really fast or like not at all. You know, this kind of thing. It's very case dependent, and we will spend a fair bit of time talking about the different cases in this lesson and in the next few as we continue to design circuits. But basically right now we just want you to know that which one matters at any point is case dependent and it can change, and that it's frequency dependent as well. The frequency of the on and off of your signal.
AC.
Yeah, because the reactance is only for AC signals.
Or like changing.
Yeah, at least in continuous state. Yeah. Okay. If you just have like a flat DC, then like yeah, it's just resistance. Yeah. Okay. Any questions? Yes. Oh yeah. Okay. Everyone okay? Okay. Good. Okay. This is a scenario of. Okay, so this is a single case. Okay, hey, ignore the diagram first. Let me talk. This is a single case of when impedance matters. Okay, ignore the diagram first. All right. So you see all this rubbish in the bottom. We don't care. Okay, I care about this wire here. This one wire. All right. Oh, by the way, this is the RC delay circuit. Yeah. So this is an ESP32 microcontroller. Alright, and I'm using it as an example of something which turns on and off real fast. Okay? Nobody cares. All I care about is that this is the power input. Okay? So I have 3.3 volts over here. Alright? So 3.3 volts just takes an ideal wire and it comes back down. And it feeds the ESP32. And the ESP32 just powers like whatever the hell I connected to it. Okay? Because someone was asking earlier, here is an RC delay circuit. It's connected to 3.3 volt as well. This is the enable pin. So the circuit, the microcontroller turns on, and then like 250 milliseconds later, it gets enabled. Okay, so like there's a delay there because the microcontroller datasheet wanted it. Alright, so this is an application of RC delay circuit, and we need it because the datasheet said so, and that's all we need to know. Okay. Anyway,
So what if we do not have that RC?
then like I don't know, something happens.
I guess the chip would like turn on and off very fast because of the instability in the power supply. Maybe.
I don't know.
Yeah,
Could be. Yeah.
What was the behavior?
The behavior doesn't matter. All we care about is that we have avoided the bad behavior. because we have put the RC delay circuit.
You can go
Yeah.
deeper if you want.
We can go deeper if you want, but like honestly, that's like a lesson 5 thing. Yeah.
So essentially, capacitors that we see in PCB, so ideally
all revolve
these are
around
people
signal filtering.
No, there are many reasons to put a capacitor. Yes, you can put it for like the signal smoothing thing, but you can also put it for this, which I'm going to talk about in a sec, and you can also put it for timing, right? You can also put it because like
Your data sheet says so.
your data sheet says so, yeah. There's probably other reasons, but like I've forgotten. Yeah.
Use it as a battery often.
No. Okay, we're using it as a battery here. I'll show you in a second. Yeah. Any questions before I continue? Okay, great. So everything here is a magic box which just like randomly wants more current every now and then. Okay? And I don't care about anything else for the sake of this scenario. It's complicated. I don't care. It can draw random current at high frequencies. Okay? And it can draw random current at high frequencies because of reasons. Okay? And it needs this current instantly from the power supply. Alright? Because it draws the current. I want the current now. You know, and you have like 10 nanoseconds to give me the current. Okay, sure. So this is a problem because I've got this long line. You can't see my finger. I've got this long line here, and this line has an impedance. It is not an ideal wire, right? Okay, so I have modeled the impedance now. So here is the impedance of the wire. Alright, so I have got the resistance, I've got the capacitance, and the inductance. Okay, so the ESP32 suddenly draws a lot of power, and we don't care why it did it. It just did it. Okay, and the current draw by the ESP32 suddenly massively increases. Okay, and this can happen really fast. So the power supply needs to be able to suddenly give you that power, right? The inductance of the wire will resist the change in current. This is the main problem. Okay, so the parasitic inductor will see this huge change in current. It's a very fast change in current, right? So like the rate of change is huge, and therefore we get a very huge reverse voltage that resists this change in current because of like magnetism. Okay, and this reverse voltage on my 3.3 volt line causes my 3.3 volt to be like 2.7 volts now.
That's big.
It's very big, yes.
Yes.
Um,
Need a constant frequency.
so in this case, the parasitic resistance and capacitance don't matter. You care why?
Sorry, what? Because resistance doesn't matter?
Okay, in this case we care about the inductance. In this case, the resistance and capacitance don't matter. We can explain later if you want, but like, it just doesn't matter.
Is it because the frequency is very high?
Okay, people care. I have a slide. I'll tell you later. Okay. Do I have two? I have two identical slides. Okay, whatever. Okay, so I'll tell you later. But for now, we care about the inductance. All right. So the way that we solve this is we put capacitors on the 3.3 volt line. So the capacitors are normally charged at 3.3 volts because the line was at 3.3 volts, right? So it's connected between 3.3 volts and ground. All right. When the voltage drop occurs, suddenly the capacitor is at a higher voltage than the external circuit, and it discharges.
For the last volt.
Exactly. So the capacitor discharges, and just like the smoothing capacitor, we like pull the voltage back up. Okay. So this reduces the voltage drop due to the sudden current change. Does that make sense?
Surprisingly.
Yeah.
Okay, so the inductor, it doesn't actually tank the current, it tanks the voltage.
It sees this change in current, and it gets upset, and then like the way that it manifests this upsetness is by like producing a reverse voltage. You know, so then across your inductor you will have like a minus 0.2 or something, and then like minus 0.2 volts, and then like now your 3.3 is 3.1, you know.
Okay,
Yeah.
But then the current doesn't get affected, right?
Oh, it does.
Oh, it does?
Is the resistance constant throughout the whole thing?
Okay, I suppose
Like in the
As in like this entire ideal trace, yes. So we modeled it as a single series resistor, but in reality, like the resistance is spread throughout the entire trace. Same for the capacitance.
So it doesn't change the thing says hell no and then gives the pushback which affects
Yes,
the
that's
voltage,
exactly.
lowers the voltage, which makes the capacitor need to fill in for the things.
Exactly, yes. Yes, correct.
What made it change in the first place again?
Like what made the current change occur?
Yeah.
the ESP32 like drew a lot of power for like reasons unknown to man.
Yes.
Yeah.
So it's like, and then just pulls more, which it did not have enough current in there.
No, it's not that there wasn't enough current. It's that the current suddenly tries to increase throughout the whole wire from the
And
supply
it's
to
like, yeah.
yes,
something.
yes, exactly.
There's not enough currently there. There's a
So the
lack.
so the inductance
So then-
tries to resist
Yeah.
the change in current.
Oh, it's like the big pull.
Yes.
Cooling of
So
the
it yanks, and then it's gonna push back against the.
yes, something.
Yes, you can think of it. You can think of it like that. That is a reasonable analogy. Yeah. What matters is the intuition of it. Okay.
Okay, that's
Change in current, the inductor not happy, reverse voltage. Okay, then you have voltage drop. Now you have the capacitor. Okay, so this is one of the very common reasons to use a capacitor on like a digital PCB, and we call them decoupling capacitors. Okay, so we need to place the decoupling capacitor as close to the ESP32 as possible. Why?
to reduce the interval between.
Yeah, absolutely. So like, if you put it too far away, then all you've done is put another wire with like very big inductors, and then you have the same problem again, right? So again, the parasitic resistance and capacitance don't matter. But okay, key thing, look at this. I've got two decoupling capacitors. I've got 100 nanofarad and a 22 microfarad. These are like, this is the kind of like size of farad that you're gonna see. You're not gonna find 1 farad, okay? But like, the reason why I have done this is because this 100 nanofarad is placed really close to my ESP32, and like the 22 microfarad is kind of like further away. So the 100 nanofarad is going to absorb very fast, very short current draws, it's really close to the chip. And then when the thing requires a huge like sustained current draw, then like the impedance like between this and like the big capacitor won't matter anymore. So like basically I'm doing this for like 2 different like scales of the problem. You can think of it that way. So like I've got this tiny like decoupling capacitor close to the chip for small fast current draws, and I've got a huge bulk decoupling capacitor which is like bigger, and that's for like bigger versions of the same event basically. Okay, and that's usually placed a bit further away just because like it doesn't need to be so close and it doesn't matter. Alright, or because I didn't have space on the PCB. Fair enough? So some microcontrollers will have like 6 power input pins. Great. Okay, so like what we would do is something very similar to this. We would have a single bulk decoupling capacitor for the entire chip, and then like we would have like 6 tiny decoupling capacitors, one placed close to each power pin. So each power pin will like have its own tiny decoupling capacitor which absorbs the voltage drop for long enough for the bulk decoupling capacitor to overcome the impedance and like get over here and fill in the rest. Does that make any
So
sense?
it's like slightly damage control for the bulk one.
Exactly, yeah. Because like if you have like 6 pins, right, then you got like a bunch of traces, a bunch of wires going to each pin, right? So that's got a length as well. You know, it's not like 2 mm anymore. Yeah, so there's some impedance there. So the bulk capacitance is going to handle the whole chip, yes. But what about the impedances of like those short lines to each power pin? That's what the tiny decoupling capacitor at each pin is handling. I've drawn a diagram, I don't care.
The tiny ones will also have its own impedance.
Imagine I've got my chip. It is a chip. Okay, it has like 4 power pins because like
Why not?
life sucks, you know. And then I've like my battery is over here. Okay, my battery source is coming from over here. So I've got this like long line that comes here, and then it splits like this, right? And it goes to my 4 power pins, right? So I can put a bulk decoupling capacitor here, and this goes to ground, right? This is a huge decoupling capacitor for the whole chip. But the problem is I've also got this line and this line and this line and this line and this line. These all have their own inductances, correct? So I have a tiny capacitor on each one of them, which absorbs the voltage drop for long enough until the voltage drop. No, until the impedance of this is overcome by this. Does that make sense?
You match it to the one over there, like just to be sure.
Yes, so I've drawn it like this, but actually this 100 nanofarad is like here, and the bulk decoupling capacitor is like here.
That one corresponds to that one.
This is this one. This is C7, is this one.
No, like from the other example.
This example?
Yeah, can you like match it? Do that one.
To this?
Yeah.
Yes. So
Like which one corresponds
So-
to
this is my huge bulk decoupling capacitor. It's this one.
okay.
Okay. Then I've got a small one, which is this one. Okay. And then like I would have one for each power pin like this. Okay. So that I can deal with this small impedance, because it takes time for the power to get from here to here because of the inductance. So this is why we would have like multiple decoupling capacitors. Okay. So this is like probably by far the most common reason to use a capacitor in your digital circuits. Okay? Is everyone happy? Did I make things worse? Is everything okay?
Sounds good. That's pretty cool.
Okay, great. And I'm going to exit and don't save because I don't care. Alright, great. Okay, because someone asked, the parasitic resistance and capacitance don't matter, but there's a reason why they don't matter. And I didn't put effort into this slide because I didn't think I'll be using it. But basically, the resistance of the trace is usually very, very small because it's copper. And copper is supposed to be conductive. So there is a resistance, yes, but the parasitic resistance is usually quite small. Alright, so it doesn't matter much. It matters for other things, but not for like fast current draws.
So almost negligible.
Almost negligible in this case. The inductance is terrible. Okay, if we switch really fast, the inductance if we switch faster, then we have a higher rate of change of current, and the inductance just grows and grows and grows, right? Yeah, so there's a bigger and bigger pushback the faster I switch. And the capacitance is also usually absolutely tiny. Not only is the capacitance absolutely tiny, the capacitance, like the resistance, is spread out across the length of the entire trace. It's not like... Does that make sense? So, because it's spread out across the entire trace, a lot of it is just like very far away. So it absolutely does not contribute at all to the decoupling.
Is it very small?
Yeah.
So the capacitance is supposed to resist like the changes in voltage, but since it's like very spaced, it doesn't really like, affect each other.
Yeah, it's not that it's spaced apart necessarily, because like in reality it's like just a bunch of infinitely small capacitors, infinitely close together, you integrate across the whole thing.
So because of that, it's like this uniform.
Yes, and like not only that, most of it is very far away from the chip, so like most of it does not contribute to decoupling much. Yeah.
So the inductance, the pushback, that's regardless of the material, right?
Yes, and
Because like if you change the current,
material.
there's the same change in current, but one is copper and one is like a different material. Is it gonna be the same?
Oh, no problem. It will always be copper. Yeah. Why would you make a PCB out of anything else?
Gold, so it doesn't matter. Back then it was gold. If gold, let's say if it's copper and gold, will the pushback be the same?
So basically, right, the conductor material will affect the resistance,
Yes.
and probably like got some like dielectric permittivity shit. But like basically,
More physics.
basically what matters is that the conductor has a resistance, yes, but you can have current without a conductor. And what matters is that there is motion of charge, not that it is through a conductor. It's just that there happens to be a conductor there,
So the motion
right?
of
So
the
so the motion of the charge is what creates the inductance. It is not the presence of the wire. Charge can move through any medium. It doesn't have to be a conductor there or not. So actually the inductance is completely not coupled to the kind of material, unless there's some like dielectric funny shit going on, which I don't care about.
So it's like
Probably some epsilon with like a knot or something, right? Yeah.
Basically, there's a certain point in time when all this shit shenanigans just doesn't apply when you're designing circuit.
Yes, correct.
Because you're basically just dealing with zeros and ones. Whatever that's going through here, right, just basically all about filtering.
For digital circuits.
Yes, we have intentionally limited the scope to digital circuits, otherwise everyone will die.
So you heard of those stories of semiconductors putting memory as close to the CPU as possible, or the PCIe card as close to the CPU as possible. It's basically all about signal filtering. The better your signal, the faster you can push your signal.
so it's like he's putting something closer to what
Yes, correct.
Analogous, but not exactly. Like
Closer.
I can see your hairline receding.
It's okay, I'm growing my hair longer to compensate.
Wait, actually, okay, you said digital circuit, right? So that means that like if the current is like, it doesn't mean because like the capacitance is like curved, but if it's like positive, like let's say it's between 100 and 110, doesn't matter. We just say it's 1. And then if it's like below a certain number, then we just zero it away.
So yes, so for high and low signals, we say that any voltage above this threshold is a 1 and any voltage below some threshold is a 0.
Correct.
Right? So some common thing that you will see is you have like voltage in like minus 0.5 volt, this is the threshold, and then like the low threshold might be 0.3 volt relative to ground, something like that, you know. Of course, it's not as simple as like it is a perfect 0 and a 1 every time, because like the way that we make a 0 or a 1 on a line is that we apply a voltage to the line, then it takes time for the current to rise, and then like it finally settles there, and then like we remove the voltage and it comes back down slowly. I mean, not slowly, but like slow enough for it to like not just be a flat change. And if it was a flat change, we have infinite rate of change of current and everything would explode anyway. So like it doesn't work like that, you know. Yeah, in real life we cannot have instantaneous like rate of change of current and voltage because there's like resistors and capacitors all over the place and inductors. So we'll go over in more detail like in future lessons, but yes, it's mostly, we're talking about digital signals, but there's still a horrible amount of funny things that can happen to digital signals, which is really annoying because like then I cannot just connect things together. I have to like connect it in a like with a certain like shape of wire, and then Penny will laugh at me and it's like it's terrible, you know. Okay, so any questions about like resistors and capacitors not mattering? Yeah.
Can I understand the last line? So
Relevant for high-speed signals.
Relevant for high-speed signal, like,
Yes. So
Should I explain that one?
sure.
I mean, there's what there? You don't know.
Where?
Don't know one.
You can write.
Isn't there a marker right there?
Okay, so
It's okay. You can
We have infinite whiteboard. Just use the whiteboard.
this one mentions like high-speed signals, right?
Yeah.
Okay, so for like signals,
Yes.
this bit here, like this thing, it is not a perfect like up. It will be like this.
Slew rate.
So yeah, that's slew rate. It's like how fast it can rise up. If you want like high-speed signals, there's so many ways of like doing that faster. That's why you can drive the thing faster, which requires a shit ton of currents. That's why like things require so much like currents to do, because they're just switching that fast. The other way is to like decrease this height. So but then the thing is that these signals, they have like sampling periods. That's like thingies where whatever, they just sample during predefined period of time. And the signal has to be ready by that time.
Yes.
But the thing is, because of this thing, especially because fluid is unperfect, you have high capacitance, it basically makes the thing from like nice sharp thingy into this. And may not be able to like meet the proper static discipline by the time. So for high-speed signals, you need to pay a lot closer attention to impedance matching and like making sure your lines are as low capacitance as possible. But then also there's the opposite of this, where it's like just it's called ringing. When you're switching too aggressively, that's also bad because yeah, I forgot. Anyways,
It is okay.
Yeah.
We will go through it in future lessons, and like we can all cry together. Okay, everything is fine.
It gets worse.
Okay, it gets okay. Realistic. Okay, to be very clear,
It gets
right?
better.
To be very clear, right? Most of the stuff you are going to be doing, unless you are doing like radio frequency stuff, which you should not be doing. Unless you are doing that, your signals are not likely to go past like what 400 megahertz. That's SPI max. That's like very fast SPI already. You know, like you're not gonna go.
USB goes up.
No, but nobody cares what you say. So basically, usually you're not going to go fast enough for some of this to matter. But so we're going to be very clear as we continue in the course what is likely to matter for you and what is likely to not matter for you. You know, some of this stuff is not going to matter unless you are doing the stupid like 5 gigahertz custom Wi-Fi.
look at me.
Just no, not you specifically, but just don't do that basically. Okay.
Yeah, if you're using most buses here, they're typically under like 600 megahertz or so it's typically okay.
Yeah.
It's only legal when they're caught.
What?
No, nothing here is illegal. It's just like whether you're gonna cry when you design the circuit or not.
Because then
Okay.
you run into all sorts of weird buzz issues and you just die.
It's like why are my bits just going away?
It is
Where are my
like
bits going?
Markers.
Yeah.
Does it matter if you like put like a piece of like an insulator between? Let's say you have you have a capacitor, you just put a piece of material in between. Does it matter?
Yeah, that's called changing the dielectric.
Or
Yeah.
Yeah. So like the changing the dielectric matters, and there's like millions of kinds. I don't know, like 20 kinds of capacitors. So you can depending on what your application is, different kinds of capacitors will be like very relevant. So usually we care mostly about what ceramic and electrolytic, and that's it, right?
Ceramic, electrolytic,
Tantalum is a subset.
Tantalum is its own thing.
Really?
Yeah.
I thought it's electrolytic.
No.
No.
It depends.
Okay, I've been lied to. Continue.
Then also for other stuff, there's film, polymer. I think there's new silicon carbide ones.
Nobody cares about the new silicon carbide ones. You can Google you can Google the different kinds, but like basically yes,
Also
you can change.
supercapacitors,
You can.
those are fun.
That's the 1 farad capacitor. Yeah.
You get 10 farad capacitor,
Okay.
but only like 2.5 volts.
I can be here until whenever.
The one you take up from
But I will meet. I will.
Nah, those ones
Oh,
are just
10. Yeah.
Not tomorrow.
Okay, sure.
Those ones aren't ELDCs, but they are very big. Yeah, like few hundred volts.
Okay, yeah, so you can change the dielectric, and like the different kinds of dielectric you can go and Google, but like usually like I only really use ceramic and electrolytic for most digital signaling. I have used like one tantalum and I was very upset about it. Okay, yeah, okay, okay, this is like, okay, so we are almost done with what we wanted to teach, and then after that we're going to help everyone install KiCad on their computers, because like we need to prepare for the, like lesson 3 onwards. Okay, so we have decided on like a few things which we are actually going to talk about during the rest of the course related to impedance, and the rest of it we are simply going to pretend they do not exist and cover our eyes. Okay, so signal integrity is basically where the impedance changes across your trace, and then this will cause like your digital signals to just like fly away. Then power delivery, your parasitic inductance, this is what we just talked about with the decoupling capacitor. Alright, then the filtering, this depends on stuff. Resonance depends on stuff. Crosstalk depends on Faraday's law. So basically it is saying that, look, I have two traces next to each other, they are turning on and off really fast, so there is changing magnetic field, and magnetic field can induce voltage in other traces, right? So this trace is going to induce a new signal in the other trace, you know. It's a weak signal, but it's still there and it's causing problems, you know. And then we have timing, where basically like you are assuming that for all of your circuits so far, you have assumed that current is like just like moves at infinite speed, but this is not true. It's like best case scenario half the speed of light, which is not fast enough for a lot of things. Okay, there's other things too, and nobody cares. Okay, everyone happy? Yeah.
What's the unit of impedance?
Impedance is okay. So impedance is ohms. It is more complicated than that because
There's complex numbers.
okay, so okay, guys, chill. I will explain. Okay, we specifically omitted like that because like we felt that it was annoying. But basically, you have resistance in the x-axis. Okay, and then you have reactance in the y-axis.
Yeah.
And reactance is summing up impedance, is summing up inductance and capacitance in like some way. Okay, and then you take the hypotenuse of those two and you get the magnitude of your inductance. Okay, and then like you have the angle between the hypotenuse and the x-axis, right? And this is the phase angle, and nobody cares about phase angle, and stop thinking about it. Okay.
It's the lag between the
I know it's the lag between the phase. I don't care. So the angle is the lag between voltage and current curve.
Yes. So with a sine wave, you get
The shift.
yes,
Yeah.
it's the shifting between the voltage and current.
Where does this angle come from again? Is it like
The hypotenuse and x-axis. Yeah.
Really? That's really cool.
Yeah.
That's really cool.
Yes.
That's bullshit.
What's the
So this way is resistance, upwards is capacitance and inductance,
So this is square
and this is impedance.
Oh.
Okay, so the length of the hypotenuse is your impedance magnitude. Okay.
And the angle is
Z is the symbol of impedance, and the JX is like
X is the
things.
reactance.
Yeah.
X is the reactance,
Okay, so
You can take EM in term 5 if you want. In term 5 EPD if you want to learn more of this stuff.
yeah, if you want to like grow and mature as a person, you know.
It's horrific.
Okay, so like the thing is we don't care about the absolute value of impedance for most things. Okay, so we care about the exact value of impedance if we're doing like USB data lines, or if we're doing radio frequency stuff. In which case everything should be like 50 ohm or 90 ohm. But like usually, there's online calculators, like who cares, right? But usually we just want the inductance to be like, the impedance to be either as big as possible or as small as possible depending on the application. Yeah, and then we just like follow rules of thumb to say, this is gonna make it bigger, and then you do it and it makes it bigger. You don't think about what the exact value is. And like in this way, you avoid most of the math when you are designing most of your circuits, and like everything is like wonderful. Yeah.
Basically, just spam the bigger it is better.
Or the smaller is better, yeah, depending.
Depends.
Yeah. Okay? Okay, any other questions? You might as well. Yeah, before we install KiCad on everyone's computer.
Does impedance behave like resistance in a DC circuit?
Yes.
Yes,
Yes.
in DC circuits, there is pretty much only, like, okay, in DC steady state, where the DC is not changing over time, yes, you only have resistance. And then, of course, if the DC is changing over time, then you will start to have rate of change of current and rate of change of voltage, right? In which case, the other two components will start to appear.
So
Yeah.
basically, an inductor becomes a short circuit, and a capacitor becomes a open circuit in DC steady state conditions. Yeah.
Ken? Anything else?
Okay, this is gonna sound weird.
Okay, so basically, an inductor becomes a short circuit,
Okay.
and a capacitor becomes an open circuit. You can see the symbol. It's like
Just like
yeah. In DC steady state, that means when the voltage is not changing at all.
Yeah. Everyone understands why, right? Okay, because when you have steady state DC voltage, you have like constant voltage and constant current. If you have constant current, you have zero rate of change of current, which means there are no inductive effects, which means the inductor doesn't care. It just lets everything through. So the inductor is just a wire now. So no inductive effects. And you have constant voltage, which means you have zero rate of change of voltage, which means no current through the capacitor. Because current through a capacitor is proportional to rate of change of voltage, right? So no current through the capacitor means it is an open circuit. The capacitor does not conduct at all.
Oh, because the voltage and the current is constant.
So like it's just steady, like it doesn't move,
That's right,
doesn't
yes.
do anything.
So this is special case where like it doesn't, only resistance matters.
So DI is 0 and DV is 0, then the whole thing becomes 0.
Correct.
Fair enough.
But in AC,
In AC, yeah, this shit like screws everything up.
they have values.
Yes.
Their values.
They are non-zero, and therefore you have non-zero inductance and capacitance effects
This
here.
refers to the current flowing through a capacitor. This refers to the potential difference lah across the capacitor.
I feel like I'm learning this the wrong way. I'm learning this before learning the thing that's supposed to go before it.
Yeah, that's why I didn't attend lesson online.
I wasn't here in lesson 1. I was like in the Philippines.
No, it's recorded. It's on YouTube.
Okay.
What is this? Oh yes. There's also.
This is cry though, like nobody cares. It's just pain. Okay,
the math matters.
alright. This is my last slide. It's gonna be the last slide, every single slide, but like basically, the point of this course is to make you comfortable with designing your own PCBs. The rest of the course is going to actually be designing PCBs now, okay? And we are going to use our link, and like you'll get like a whole bunch of money off your PCB, okay? Like depending on what your PCB is, it can be really cheap or really expensive. So like don't spam too many things, but generally you'll be fine, okay? Because you are unlikely to be doing any complicated projects, okay? Okay, who has laptop?
Install KiCad.
Okay, everyone is going to install KiCad right now.
Oh, can I get added to the space bar? I did. Oh, you did.
Yeah.
Yeah,
So everyone's just gonna design the same thing.
Why?
Then you're gonna order one.
You don't have to order. You don't,
I thought you're gonna order.
you don't have to design it. As in, you don't have to order, yes, but you also don't have to design the same thing. Like, I don't care what you design. We'll guide you no matter what. Yes. But like, you design whatever you want, and then like, just don't populate order or whatever. Or solder yourself. We'll teach soldering at some point. Okay, so here's KiCad, KIKAD. Bye bye. So KiCad is the schematic design software that we are using. Okay, so here's KiCad.
Penny.
Bye bye.
Bye.
Okay, so Google KiCad and then like go to download Lamau. It's really not that hard. Hey, wasn't this a GitHub page last time? Did it get better?
I mean, it's more
Oh, it's still a
downloads.
GitHub page. Yes. Okay, fine. Okay, go and find this. Go and find this page. So click downloads and then go to whatever OS you have. Most likely Windows. I don't see a single Mac.
Or download.
Yeah, download for Windows. Yeah.
Pin price display.
I don't have my laptop.
Don't worry. You don't need us to walk through it. Like you'll be fine.
No, it's like coordinate transform for
Yeah, yeah.
Spherical coordinates.
The probably like hit. And so for basically you know Snell's law. Basically you know Snell's law. That also applies for that also applies for RF.
Wait, so when you talk about RF, you're talking about EM.
Yeah. Snell.
Don't want to do
So sine of omega t is like you do like some sort of is it related?
I don't want to do that.
I mean like the square wave is
Yeah, just the odd harmonics. What is it?
telegraphy equation.
Does everyone see this screen?
Telegraphers.
What is this with respect to second derivative of voltage?
It's the phasor. These are the phasor forms.
Okay, so
Phasor, so like there's an angle.
okay, so we have a bunch of stuff here. We only really care about the top four. Okay. The rest of them are for like stuff and like it's not a problem usually. Okay. So the schematic editor is where we do the schematic. So this is like where all my example circuits have been coming from. So a schematic is an ideal graphical representation of what connects to what. Okay, so like this is how we design circuits. We start with the schematic. We say, look, I put a capacitor here, an inductor there, a microcontroller there, you know, and like everything connects together in the schematic first. But this is only an ideal graphical representation. Then we go on to the PCB editor, which currently has nothing like for at least for this project. But basically, the PCB editor is where we actually connect things in like real space with real dimensions. You know, the schematic doesn't know how big a capacitor is, how big an inductor is. It doesn't know how far apart we put them or anything. So we arrange them in three-dimensional space or 2D space if it's on a board. It's usually on a board, right? So then we arrange it in 2D space on the board, like in the PCB editor. Okay, so I'll show you an example and like, be not afraid. But like, here's an example. So, what's the least bad example I can use? Okay, sure. So here's a schematic that I made. It's like the third schematic I ever made, and it's I know it looks fine, but trust me, it's terrible. Okay. And then so we take the schematic and we have this is just graphical representation of the circuit. Then we go to the PCB and here's the PCB, right? And do not be impressed because I guarantee this is the worst PCB I ever designed. Second worst.
This is the first one you made?
No, second or third. No, the second one I threw away. I didn't even try it. Yeah, it was like that's so this is how we like actually arrange. This is an Arduino. Like this is how we arrange all the components in real space, and these are the wires that connect them together. So we call the wires tracers. Okay, it's a wire. Okay, we just call it a trace. All right. And all of these are the components that connect it together. I have a 3D viewer here. I can look at the board in 3D, you know. So this is a capacitor, right? Big electrolytic capacitor, which actually did not need to be in the circuit at all, and bunch of other stuff, right? So this is the PCB editor, okay? So next lesson, we're gonna be playing a lot more with the schematics and the PCBs. We're gonna start designing real circuits. So the default option, if you don't know if you don't have anything that you want to make, we are going to show you how to design an ESP32 development board. And trust me, that is like quite simple. Don't worry, okay? If you have something specific that you want to make, we are happy to help you with that. Like, because everything will be quite like one-on-one. Me and Joseph will be walking around a lot. It will not be like one guy at the front anymore, okay? Because everything will be hands-on from now on, okay? So if you want to make something, just make it, and like we'll help you along the way. Next lesson will be about how to use the software in general. Then after that, we're gonna go on to power supply design, because every circuit has power supply. And then we are going to go on to microcontroller basics, which Joseph will be mainly teaching. And then communications, which Joseph will also be mainly teaching. And then we're gonna talk about a bunch more impedance stuff, like trace shape and like why your ground is not actually ground and whatever. And like that will, after that, we'll teach you how to order your board. Okay? Any questions?
Oh, the things get like after you printed and
Yes. I have quite a lot of PCBs just lying around now. Yeah. Yeah.
And if you want to make it into real life, you have to go to like a China company somewhere.
No, you just send it online. You don't need to go to China. No problem. Okay.
from China.
Yeah,
Yeah,
we'll
but
we
it's
yes, and they will mail it to you. Okay. We'll teach you. No problem. Okay. There's one like lesson. The whole of lesson 8 is teaching you how to order a board, and then lesson 9 is analog. Okay. Yeah.
Wait,
Which Joseph wanted to teach.
I'm looking forward to it.
How many lessons will we have? Because it looks like if once a week it's gonna run into term 2.
So what?
I just checking.
Yes, we will run into term 2. Yeah. Okay. Yes, there are 9 lessons total. Okay. Any questions?
Did you do lessons for 3D printing also?
Yeah, so I also teach a yearly mechanical lecture series. I just finished teaching it like 2 months ago. I'll start teaching it again like sometime in term 2, probably concurrently, usually on Tuesdays, which is why this is on Mondays. Yeah.
Yeah, I remember walking into one of the classes you had last time, right?
Yes, that's my mechanical series. Yes,
Okay.
which is also 9 lessons.
I see. Wow, you do this like every year?
Yes, this is the 3rd or 4th year now in SUTD. Yes.
Oh, wow.
Okay, great. If that's all, then I've got nothing else for today. We'll just end early and then like go back and think about what you want to make. And if you need ideas, we have ideas. Yeah. Okay. Okay. Bye bye.
Where did you get this from?
That's all, yeah.
We didn't end up using it though. How do I close the live stream?
Okay.
Why is there no hang up button?
OBS.
OBS? I have OBS now. Is it the wheel?
Yes. So you just
Oh, so we will just record.